Hello, in this video we'll be talking about section 2.3, Systems of Linear Inequalities in Two Variables. First of all, a linear inequality is similar to a linear equation ax plus by equals c, but with the equal sign replaced by an inequality sign. This could be a less than, a greater than, or a less than or equal to, or greater than or equal to sign. An example is 2x minus 3y less than or equal to 6. Often, a linear inequality is written in slope-intercept form, like y greater than or equal to 2 over 3x minus 2, where 2/3 would be the slope, negative 2 would be the y-intercept. An ordered pair is a solution if it makes the inequality true when we substitute in values for x and y, and we end up with a true statement. This is very similar to linear equations. However, it's not that we want the two sides to be equal to each other, we just want the inequality to be factual, which means we want any solution where one side is indeed greater than or equal to or possibly less than the other side. To demonstrate this, let's look at an example for the inequality x plus 4y less than or equal to 4. Any point along the line x plus 4y equals 4 will satisfy the inequality because the inequality symbol includes equality. So we begin by graphing the line. You can use the x and y intercepts for this equation to graph the line. For example, if you find the y-intercept by finding x equals 0 and solving for y. We can demonstrate this here very quickly. Let's take the equation version of this, x plus 4y equals 4, and plug in 0 for x. That will just give me 4y equals 4. And I can divide both sides by 4 there to get y equals 1. This is where we get this point or ordered pair of 0, 1. You can do the same thing to find the x-intercept by plugging in y equals 0 and solving for x. We can then graph this, which we can see below on this page down here, graphed like so. We have the points at 4, 0 and 0, 1, and then the line drawn between them. Then, if we want to find other values that satisfy this, because remember that we're not looking at x plus 4y equals 4, we're looking at x plus 4y less than or equal to 4. That means we want to check other values which could be on either side of what we'll call the boundary line here. So, to do so, we'll take that boundary line and test a couple of ordered pairs, one on each side of that boundary line. First of all, if we substitute, let's say, -1, 3, which you can see down here, would be above the boundary line. You can test any point, but let's test this one. If we plug that into our inequality, what we're going to end up with here is 11 less than or equal to 4, which is not a true statement. That means that values on that side of the boundary line are not accurate. We can then test something below the boundary line just to make sure that we did good work there, and we could test, for example, 2, 0. If you notice that on the original graph, that is below the boundary line. And this would be a nice convenient value to use because one of the numbers we're plugging in is just 0. If you do plug in 2, 0, you will end up with 2 less than or equal to 4 from your inequality, which is factual, meaning that values on that side of the boundary line are correct. So we can then create our new version of this graph. The boundary line, as a reminder here, is the dividing line between the solutions and non-solutions. We'll call each side of those the half plane. So we're looking for the half plane that has our answers, and that should be the half plane that includes 2, 0. This is why in our version of the graph here to represent the inequality, we have our full solid line there, and the half plane below it that is fully shaded. Let's review a few of the terms that were discussed there. So first of all, we have that a linear inequality is an inequality that relates linear expressions with two variables. Note that it relates them, it doesn't have to be equal to them. It could be less than, greater than, or what have you. We then call the boundary line the thing that divides the coordinate plane into the two half planes, one of which represents solutions to that inequality. If the points on the boundary line satisfy the inequality, then the line is drawn as a solid line, like in the previous example. That should happen when you have less than or equal to or greater than or equal to signs. However, if the points on the boundary line do not satisfy the inequality, we don't want to represent the line itself as a set of solutions, so instead we're going to use a dotted line in place of that. Solutions to the linear inequalities with greater than or less than do not include points on the line, so should be drawn with a dotted line instead. So let's demonstrate this. With these two problems, you'll notice that they have very similar looking equations. The first problem says to graph 2x minus 5 equals 3. The other one says to solve 2x minus 5 greater than 3. Very similar. One is an inequality though. That means that for problem 2 there, we're going to draw our line and we're going to have to shade one side of the graph there once we divide that into the two half planes. First though, let's just graph 2x minus 5 equals 3 as a full solid line for problem 1. You'll notice though that is 2x minus 5 equals 3, meaning there is no y value there. So this is actually going to end up as a vertical line, something where we have x equal to a consistent value, and that is all we have. So I'm going to take that equation we have of 2x minus 5 equals 3, and I'm just going to try to get x by itself there. If I add 5, that will give me 2x equals 8. And then I can divide by 2 in order to get x equals 4. That means that x is equal to 4 is always equal to 4, no matter what y is. So I'm going to draw that like so. At x equals 4, I'm going to just draw my vertical line in that way. Now if we do that with an inequality, we can do the same process. 2x minus 5 greater than 3. I can solve for x there by adding 5. And then dividing by 2 again will just give me greater than 4 this time. This means I'm still going to draw a line at x equals 4, but because it does not say greater than or equal to 4, I'm actually going to draw a dotted line or a dashed line, like so, at x equals 4. This is not my final answer though, as I do need to shade what side of the half plane would give me solutions for this inequality. We can test a couple, for example. Let's say I test x equal to 7 and see if that works. I could put x equal to 7 in my inequality, 7 greater than 4, and that is a true statement. That means that that number should work. Just to ensure though, I could test something on the other side of this. Let's say x equals 0 is a nice easy one. If I try to plug in 0 into that inequality, I get 0 greater than 4, which is not true. That means that should not be a true value, so I want to shade things to the right side of this vertical line. I'll do so with a blue shaded pen like this. That would represent my set of solutions here. Hopefully that gives you an idea of how we will approach problems for systems of linear inequalities in two variables. Have a nice day.